Hi, I am Selva Prabhakaran. Previously, we saw the measures of central tendency, which is the first part of univariate analysis. Now, let's look at the measures of dispersion. Again, there are two types of measures here. The most commonly used ones are the absolute measures of dispersion, which are the range, variance and standard deviation, and quartile deviation, also called as the interquartile range. Inter, I-N-T-E-R, quartile range. Interquartile range. Let's understand this. Let's say you have a particular variable. I'm going to draw out this variable. Imagine this to be one single column in a larger data set. Let's call this column as x. And the values here as x1, x2, so on and so forth. We have all these values filled in. The range is nothing but, range of this particular variable x is nothing but the maximum value of this column minus the minimum value. That is range. Variance, on the other hand, variance and standard deviation are very similar. Variance is nothing but, for the entire data, we compute the mean. Let's call the mean as mu. For every row here, every observation here, we subtract the mean from it. So x1 minus mu, x2 minus mu, so on and so forth. For every other observation, we do this. Then we just sum up all of these values and divide by n. So net, the formula for variance, we write it as sigma square equals to xi minus mu the whole square. You take a sum of this where I equals to 1 to number of observations n. I forgot to add the square here. We should square all of these terms and then sum it up, right? So we square it up, sum it up, divide by the total number of observations, that would be n. This is the formula for variance. Now, if you take a square root the whole term, that would become the standard deviation, simply written as the sigma term. This is nothing but standard deviation. Now, standard deviation sort of tells us how much the data, suppose we have the mean for the data here, right? This tells us how much the data spreads from the mean. That is represented as standard deviation. If the standard deviation is small, the spread of the data will be small, right? So that is variance and standard deviation. Quartile deviation or the interquartile range is nothing but, let me erase all of this. Say you have the data, all right? Let's imagine you had the original data previously. Now let's imagine the x column here is sorted in ascending order. So the lowest value will come here, keeps on increasing with the highest value to be in the bottommost. Now we have sorted this particular column and we split this into 4 parts. We split this into 4 equal sized parts. So suppose 100 observations means 25 observations here, 25 here, 25 here, and 25 here. Now, this particular value here is first quartile, this is second quartile, this is third quartile. The difference between the third quartile and the first quartile, which is Q3 minus Q1, is nothing but the interquartile range, as it is commonly called, also called as the quartile deviation. Alright, so all of these 3 measures tell us how wide the data is spread from the mean. So those are absolute measures. Now what are relative measures? Previously we saw the absolute measures to be range. Here we have a coefficient of range. Now let's say the range is, say, 500. The range is 500, all right, which is nothing but the max minus the minimum value. But imagine this 500 alone does not tell us the entire picture, because say max could be 1000 and minimum could be 500. This also gives you a range of 500, whereas the max could be, say, 10,000 and minimum could be 9,500. Here also the range is 500 only, but it is not so much spread here. Getting me? As the scale of the data changes, the range does not tell us the entire picture. That's why we have something called the coefficient of range, which is given by the formula, nothing but range range divided by max plus min. So let's say we had two cases, right? So minimum value was 500, maximum was 1000. Another case where we had the minimum value of 9500, maximum was 10,000. Now compute this. For the first case, it would be 500 divided by max plus min will be 1500, right? For the second case, it would be again numerator is 500 divided by 10,000 plus 9,500, right? So that would be 19,500. Now this value is way smaller. This is way smaller than the second value. Now this here represents, this is a very small value, right? This here represents that the range is actually very small compared to the scale of the data. In my opinion, this is more meaningful. Likewise, we have something called the coefficient of variation. This is a proxy or a relative measure for the variance or the standard deviation. So this is nothing but, earlier we computed the standard deviation, right? We divide the standard deviation by the mean of the data and multiply it by 100. That is nothing but the coefficient of variation. Now the advantage here is, say previously you determined that the standard deviation of a particular variable is 20, let's say. We don't know if the standard deviation is large or small. If the mean of the variable was say 100, we know 20% deviation exists. Whereas if the mean of the data was 1000, this is not much of a deviation, right? It's a very small quantity. So we divide by the mean. That will give us a percentage, that the spread of the data is shown as a percentage when compared to the mean. That is the advantage, and this gives us the real picture of the spread of the data. In a similar sense, we have the quartile deviation. Let me erase this. We have the quartile deviation, which is Q3 minus Q1 divided by Q1 plus Q3 by 2. This also serves the same purpose as the other two variables. But amongst the three, in my practical experience, we normally compute the coefficient of variation very, very frequently. Whenever you compute the standard deviation, this is usually what is reported when you compute, say, the description of a particular column in Pandas or any of the packages. This is computed, but in addition to this, it is customary to compute the coefficient of variation also. And more or less frequently, we also compute the coefficient of range as well. So given a data set, combining the measures of central tendency, which we covered earlier, plus the measures of dispersion that we have just computed, we compute both of these sets of metrics for all the columns in your data, numeric columns in your data, and that would complete what is called the univariate analysis.